waves. And so some major discoveries go on here in one fell swoop here. But for those of you who don't know, and here's the preview, we are going to calculate the speed of these waves, and they actually come out to be the same as the speed of light. And so we already knew, and Maxwell already knew the speed of light, and so that's why he was so amazed when it came out to be the same number. And so not only could communications exist, but they could exist very fast. And it also gave, for the first time in history, an answer to what really is light made out of. Anyways, but there's the first part of this, A. What is the speed of these things? So this is the speed of light. Here's one that we're going to talk about. What is the wavelength of these? And what we're going to do is we are going to then draw a picture on Tuesday and say velocity is distance divided by time. If you let these things travel one wavelength, the time it takes would be one cycle, or a period. And what's the reciprocal of a period? Yeah, it would be frequency. So frequency times wavelength would be their velocity. And we just said their velocity was c. So to answer this question, what is their wavelength? We would get c divided by their frequency. That's obnoxious. All right. And so in this case, it would be 3 times 10 to the 8th meters per second. And this might be the harder part. We'll talk about the radio dial. But if somebody were to tell you the radio station was, in this case, 64 KFI, or maybe I'll make it a little bit easier. Somebody said the radio station was K-Earth 101. What's the frequency? 101 what? Megahertz. Now the AM dial we haven't mentioned. I've done a few of the FM dials. But 64 KFI means 64. And it's a little annoying, because it's not quite kilohertz. It's 10 kilohertz. All right. So,
Are we going to have to remember that?
No, you won't have to remember that. All right, but we'll get the radio out Tuesday and we'll play with the little dials there. But if you look at them carefully, you'll see those little numbers. Next time you look at your radio and you dial in K-Earth, look down on the side, and I bet you'll see somewhere lit up really small MHZ for 101.1 megahertz. In either case, then, that answers our question about what is the wavelength of these things. And since a little low on time, and you guys have the solutions worked out for you there, I'll go ahead and leave that one and let you calculate whatever that wavelength comes out to be. And of course, probably the hardest one is the one we've already touched on right here, which, like I said, now that I give it more thought, I really don't think we'll get this far on Tuesday. This would be section 4. And it asks, what would the voltage be if you made an antenna that was 65 centimeters long and you were 200 kilometers from the transmitter? And so since it's time to wrap up, why don't I just say, look back on your notes for when we did this on the first one. You'll remember it was C times the energy density. And the energy density we could write as 1/2 epsilon naught times the electric field squared. And the intensity we could write as power over area. Oops. Oh. And so let me put in some numbers. What was this? Oh, that's their slogan. I guess I should know it, right? KFI. Coming to you at 5,000 watts of power. All right, or no, 50 kilowatts, something like that. Anyways, so they're 50 kilowatts, which, by the way, if any of you are curious, is I think the only radio station that is got a FCC license of this much power, because they can transmit all over the United States. And so all the other ones are much, much less powered, and they are not designed. So there's nobody else on 64. You can be in, I've been in Montana before and picking up KFI, you know, and saying, all right, hey, coming out of LA. And so broadcasting out of LA, but you're in Montana there. And then the area is 4 pi. And of course, now we're a good distance away, 200 kilometers. No. And so let me write it as 200,000 meters. Let me write this as 3 times 10 to the 8th. Let me write that as 1/2. Let me write that as 8.85 times 10 to the minus 12. Let me write this as the maximum field squared. And then, just to kind of wrap it up, I won't actually do the number, but if you get out your calculator, that will give you the electric field. And so the last step, which, like I said, don't think we will actually get to, is to say that the electric field times distance would be the voltage. If this is the maximum voltage, it does change with time. And then, so this length is 0.65 meters. Yes? Yes. Yeah. This I would say is coming from chapter 26, where it's the integral of E dot dr. And although it changes with time, but the electric field is the same over that space. So at that moment in time, it would be a constant, so it would just be E times L. All right, well, I guess we'll call it good. And we'll keep working.